you again for the introduction. And when team reached out to me to give a talk here, I was thinking, what should I talk about? I could go like each protocol that I was working on and like go deep into the details, but I decided that would be a bad idea because first of all, I don't remember the details and I was too late to remember them. That's the honest answer. But you know, the regular answer is that we are short on time, we can read all details. So yes, that's the regular one. So I decided instead, just take the opportunity, like kind of recap all the stuff I was working on the last like 18 of my years in the industry working on BFT protocols. Which I thought was going to be a good exercise for me, even though preparing the slides would be much longer than I hoped to. And then just kind of go through that on a high level, try to give some intuition about the things we did, the challenges we faced, without going into it. But I do want to try to keep you guys engaged as much as I possibly can at this moment. But we'll see how it goes. You're welcome to ask questions at any time. If I know the answer, I happily answer. If not, I will give you something confidence, with a lot of confidence. Let's see, how it goes. Okay, so consensus, simple definition, right? We have safety and liveness, simple purpose. Safety will say something like, honest nodes do not disagree, never agree on conflicting proposals. Liveness said that eventually, honest nodes will out something. This is kind of neat. I mean, not this specifically. This is like not formally. That's not formal enough, but you can make it kind of neat. But then we'll start asking questions. Which consensus are we talking about? Is it single shot? Is it multi-shot? Even if we say single shot, then there is a and node. Each was an input proposal. Communicate to agree on output. Yes, safety and liveness. But what about validity? Now you start asking yourself, which value is okay to agree on, right? And you have so many options. Strong validity, weak validity, external validity. You're already starting to get busy, but that's not all right. If you're talking about the blockchains, you actually need a multi-slot consensus. Single consensus is not good for blockchain. You are building a chain. You need a repeated consensus, which we call multi-slot consensus. So, end nodes communicate from an ever-growing sequence of blocks. Again, safety and liveness are fine, and you probably pick an external validity for this task, which means that in your block, all the transactions there, if I see them, I can verify them. Usually, we just client signatures. This will make the proposal valid and the block valid. Oh, that's all good. We have a definition. We can work with it. Not quite, because this definition hides a lot of stuff from you. For example, what are the model assumptions? So there's the network. Do we consider synchronous network? Is it good for us, right? Can we rely on synchronous network for safety? Maybe not, maybe yes, depends what your beliefs. Do we want to do partial synchrony instead? Or do we want to go for a synchronous consensus, right? This is like some of the questions you ask yourself when you design a consensus for the cryptography. Do we believe that the person is computationally bounded? Or do we, or don't? We can do information theoretical consensus. Do we need a trusted setup? Can we trust a trusted setup? You start asking yourself all these questions. There's already a lot of options. Then you go to resilience. We know that 3x+1 is optimal for partial synchrony, but we also know that if we can relax that and do 5x+1, we can do consensus faster. So again, you ask yourself, right? It's a trade-off, right? So you end up with a huge design space with this consensus. Which one should I pick and which one should I deploy in practice? With a lot of questions. Luckily, this is why we all have jobs here, because otherwise it's all been solved like 10 years ago, right? So, and this is what my talk is about, right? The consensus keep evolving. Even though we keep thinking that's the end, somehow a new requirement kicks in. Sometimes we reinvent the wheel, actually most of the time. Sometimes we don't, but the requirements keep changing. So even if some experts will say, oh, this thing was already known 20 years ago. Not quite, because the setup probably changed a little bit, and it's not the same people working on it, so everybody thinks they are inventing it from scratch, including myself. I'm not excluding myself from this criticism, never. Okay, moving on. We have the performance question. We are talking about deployment in production, right? So latency and throughput, two metrics. Now, when we talk about latency, do we consider end-to-end latency, or do we only talk about block time? No, in blockchain we say how fast, actually not sure what the definition of block time. This is the Solana people invented this. It is amazing marketing. But to my understanding is how fast can I propose a block? Why is it useful? I was trying to understand for 2 years, maybe Roger had a better idea. But yeah, there is this block time thing. Now you also ask yourself, do I care about common path latency or do I care about recovery path? 99% of the time, you will care about the common path. Well, it depends how good your engineer, maybe it's going to be 80%, but most of the time you're going to care about common path. Sometimes you will care about recovery path. And there's again a trade-off. If you want, you can have your common path very fast, recovery very slow, or you can be in the middle. So there are a lot of questions to ask here in performance. Then you go into P50, P90. Do I care about, when I care about the latency for a transaction, do I care about the medium latency, the average latency, or do I want to guarantee that 99% of the transaction are going to go fast? It's again, like you won't believe how we changed the design. I'm sure Alberto has much to say about that, and I have a feeling. Okay, now throughput. How many validators when we talk about like high throughput for 10 validators is completely different game than high throughput for 100, 150 validators. Again, Alberto is agreeing with me over here. So then, is it a peak throughput? Can you sustain the peak throughput? Or how long we can sustain a peak throughput? Also, is it amortized throughput or an average, amortized average throughput or just a constant throughput? Then I say some protocols, they know during the asynchronous period, they are gonna accumulate some throughput non-committed. When synchrony will resume, they were committing a lot of throughput, right? A lot of transactions. Then they're gonna say our average throughput is that high. But it's not true, right? I mean, because it's not very useful for blockchains, at least from my experience, because the bottleneck is usually execution. So execution will determine the end-to-end throughput of the system. So if execution can do, let's say, 100 transactions per second, consensus will give execution 100 transactions per second, that's perfect, right? The whole system is 100 transactions per second. But on the other hand, if execution sometimes give you 50, sometimes will give you 150, on average, 100 you think all is good, but it's not good because during the period when it's 50, the execution is not saturated, but you cannot recover this time. When the consensus will give the execution 150 transactions per second, execution will say, sorry, I cannot do more than 100. I mean, it's nice that on your paper you claim average throughput, but what am I going to do with it, right? So all this stuff, it's a lot of points for consideration when you design a BFT system. And I mean, I wasn't born with this knowledge, it's just I was forced to learn this by working like in an industry where we actually deployed BFT systems, which was very cool experience, by the way, because you get to work with engineers. They didn't get it's interesting, right? Really, from my perspective, they didn't get the proper training, they didn't do PhDs, they didn't attend these talks. But somehow, and I'm telling you with confidence, they're better than me, they're better than everybody in understanding the intuition of consensus. They cannot formally prove things, but they very rarely wrong, and they understand their consensus really, really, really good. Like what will work, what will not work. You can come up with them with a beautiful protocol, you publish the paper in CCS, you're so happy, right? You're so important. Then you come to them, it's like, this thing is not gonna work, never, don't waste my time, go, right? And then you talk to them and try to understand, and usually they're nice stuff to slap, so we come up with something that will work. Most of the time it's their idea how to make it work, and it works in the end. So that's my experience.
This is for engineers criticizing your protocols, but what about the other way around? They come up with a protocol, then you look at it and...
Yeah, I know what you're talking about. Yeah, sure, it goes both ways, I agree, I definitely agree. Okay, so let's move on. Oh, I forgot about this. Sometimes, when I'm talking about properties before, sometimes we can come up with new properties. It's not only about liveness, safety, and validity. There is this thing that called censorship resistance or resilience, which is becoming more and more important these days, and order fairness, which I'm not sure if you can actually formally define it. I saw some attempts. I didn't like any of them. But yeah, there is also this property as well. And then when we design our consensus system, like I said before, we need to understand where we want to be, and we're going to design it accordingly, and it keeps changing. It keeps changing, that's my point. You design a protocol, by the time you are starting deploying it, requirement changes, and you need to redesign it and move on. So, which is nice because we have a job, but it's also a bit sometimes frustrating. Okay. So yeah, that brings me to the goal of my talk. I'm going to share with you my understanding. Different people have different understanding. I'm not claiming to know everything, just my understanding of the evolution of blockchain BFT. Like I said, I spent 8 years in blockchain industry working on BFT protocols, constantly jumping from theory to working with engineers on productionizing stuff on the start, back to the theory, back to productionizing stuff, which is like a never-ending cycles of idea, changing requirements, trying to productionize, see that stuff doesn't work in production, from like 100 different things that we couldn't see. Yeah, so the goal of today is to walk you through my insights and my understanding over the years, talk about the changing requirement, and I want to touch a few innovations that we did along the way. I won't go deep into the details. I said before, I don't remember them. And but if you have any questions, please feel free to stop me anytime. I will really try to remember. Okay, so BFT wasn't the first consensus BFT protocol. It started, I believe, in 1982, right? That's the year when Lamport and others came up with Byzantine generals. But BFT was really the first protocol that did a system. A system paper that demonstrates it can work, it can have a decent throughput, decent latency, and putting it back to on this like big design space, it assumes partial synchrony, optimal resilience of F, and 3F plus 1, optimal theoretical latency, which is kind of interesting, 3 hops, right, for this resilience, and they have 2 variants with and without signatures. Then on my journey. Fast forward to 2022, I joined Novi. In between, there's huge amount of research. I will not cover this research, but a lot of research and everything we did and others build on top of this research, or builds on top of this research. So many great people did many great work. I'm saying it like not cynically. I really believe this. Jumping to Novi, I joined Novi. At this point, Novi's goal, surprisingly as it is, was to commit 1 transaction per day. That was the goal of the product. The end, nothing to remember then. The end, and Novi was about to, right? They just wanted to settle everything they do with 1 transaction per day on the chain. So latency and throughput were not really an issue. A reasonable scalability, sure, but even though I don't understand does it even matter, like when you commit 1 transaction per day. And they wanted something simple, they can maintain, no issues, right? So they chose hot stuff. Okay. Then, like I said, the initial goal was 1 commit transactions per second, but where the research lab. Where at least for blockchain consensus researchers there, we have to do something, right? So we just said, okay, let's work on latency. Otherwise, while these guys are telling us, let's improve latency, why not, right? Wait, before that, I jump ahead. I wanted to say something, a few things about hot stuff. So hot stuff is a linear protocol with 7 hop latency. Remember, BFT was a 3-hop quadratic latency, and then hot stuff innovation was to make it linear. In return, they paid in latency, 7-hop latency. Like, from a theoretical point of view, it was very challenging, right? It requires like a lot of thinking by smart people, including Itai over here, and they came up with a very nice protocol. Right? The good thing is that it's very simple. The bad thing was that when you actually start caring about this stuff, it had high latency and low. And I say linear in quotes because the paper is linear, everything in the paper is linear, but when you come to deploy, there are a few things in consensus protocol. There's the common path, recovery path that I talked about. And in this leader-based protocol, there is also a synchronization part, in which you need to synchronize the nodes after the common path before going to the recovery path. They all need to kind of loosely agree on where they are in their life, what view. So in the paper, they kind of abandoned it. They abstracted away they called it pacemaker abstraction, and they didn't talk about how to implement it. When the Facebook engineers came to implement it, they realized this thing is quadratic. And I know there are some follow-up works that try to do it linear, and to some degree, at least in theory, they succeeded. I'm not saying it's not possible. But from an engineering point of view, this thing was completely quadratic, nothing else made sense. So, yes. So like I said before, we had a research team, we had to work on something, and we chose to work on improving this latency. Oh, one more thing about the hot stuff paper was very good. I'm not sure they introduced it. Did you guys introduce pipeline, or it was pipelining was before I introduced it somewhere else?
I think it will be Talikwa.
So anyway, I'm not interested in giving credit and deciding who did what, but the pipelining idea was really, really strong in this paper. The idea is that you don't need to wait until the current block is committed before you can already propose the next block. And I will explain in a second why it's actually important. If you can understand, this relates to the block. This relates to the block time, right? You can start and you can submit the next block, propose the new block before the first one is committed. The way it works is that in hot stuff in general, you have a leader sending a proposal. Everybody gets the proposal, they sign it, right? Then the leader aggregates all the signatures of the QC. Then the leader will disseminate the QC again, and we are repeating this pattern. And this variant of hotstop that Novi guys implemented was every round it's a new leader. So kind of rotating leader thing. And so once I'm a leader, I propose in my block, everybody signs, and it's signature to the next leader aggregates it. And then in order to commit, there's one more hop. It needs to send the QCs to everybody else. And already during this time, you already piggyback its own proposal and start the next block already. So this is pipelining. And this was very cool and useful. Okay, so we started working on latency. At this point, we're still living in the theory world, and it's very important for us to keep the linearity of the protocol. So what we did is the following simple observation, which I kind of already talked about. The view synchronization is quadratic. The engineering said it's quadratic, don't mess with it, it is what it is. Don't talk to us about it. Okay, so if I need to pay quadratic cost before I do my recovery, what's the point to have a recovery linear? This is like kind of stupid, right? And then we said, okay, if we don't need the recovery linear, we can go back to a PBFT style view change, right? Recovery path, and we can reduce the common latency to 5 rounds. So with Jordan, we have 5 rounds instead of 7 common latency paths, and then the recovery is quadratic. So that was the, I don't remember if somebody got promoted, but this was the protocol, and eventually we deployed it. We deployed this change, everybody were happy. Okay, now this is an interesting part, the linear replication, because first of all, recovery is expensive. I said, not only because it's quadratic, it's actually the less expensive thing in it. Recovery is expensive because when you have a bad leader, you pay the timeouts. And in this protocol, you actually pay 2 timeouts. I'm not gonna go into the details, but because you rotate leaders, you if you have a bad leader, the next leader is gonna suffer as well because he doesn't get the block from you, right? So you pay actually 2 timeouts. This is really bad, much worse than the quadratic communication. You wanna avoid it. Yes?
So on the previous slide, you said, okay, let's go back to BFT. Yeah, so it's 5 hops now instead of 3.
Yes.
What's better?
Yeah, 5, no. 3 is PBFT.
Yeah.
You cannot do better than that if you have 3F plus 1 resilience, right?
But this is 5, so...
Yes, this is 5 compared to the 7 of hotstop, of the original hotstop.
So PBFT was quadratic communication, had
Yes.
3 hops, and this is quadratic and 5 hops, so how is this better? Or do we win?
Nothing is better than nothing. Everything is the same. Let's first of all agree on this fact, okay? Then, PBFT is quadratic communication, both common path and recovery path. This is still linear on the common path, but I will get there.
Yeah, I guess also a related question is like, what was the value of linear communication? Like how important was it from the engineer's point of view?
We will get there as well. So, spoiler, not really. Okay, but it looks very good in theory, right? And the belief was that if I have linear communication, the throughput is going to be better and I will be able to scale it to more. Now, I don't want to say it's completely useless because I'm going to be lying to you. If you try to scale thousands of validators that nobody did so far, like Ethereum does it, but they don't want this kind of protocol, right? So if you try to do that, then probably linear will start to be better. But nobody ever did this experiment, it's too expensive, so we don't know for sure, but I mean, it's reasonable to assume that if you really go to a really big number of validators, it will start being important. But I'm jumping ahead, and yes, with 150 validators, doesn't make any difference. Okay, so where I? Okay, leader replication. Yes, so that's another story. So we came up with all these. We work on consensus. We optimize latency. We optimize throughput. We do this. We do that. Right? This optimization by itself, by the way, done by the engineers, which was much more impactful than anything we do. because they understood like the problem. They didn't think of like, formal definitions, formal solutions. They just said, we don't like when leaders are falling behind. We have a geo-distributed system. Some leaders are sitting in Australia. Sometimes they're too slow. They cannot come in time. We keep time out in this Australian node. This is really bad for us. We don't want that. Let's make sure we don't have this timeout penalty like every 5 blocks. Okay, what do we do? So these guys introduced the leader application. We, by the way, later published the paper on that, right? But these guys introduced it. So yes, recovery is expensive, more communication, wait for timeout, we don't want that. And so what they do, we have consensus, right? We actually have consensus, so we can use the consensus. So every time we reach a consensus, it's a deterministic point of time. I'm gonna repeat this later in my talk again, but it's for your intuition, it's consensus. Everybody gonna agree on the state at this point of time. Maybe some will reach the consensus later, that's okay. But at this point, our state machines are gonna be exactly the same. So we can deterministically agree who is gonna be the next leader. Right? With partial synchrony, we usually say we have a predefined mapping from rounds to leaders, right? But it doesn't mean we cannot change it on the fly. We have consensus. This is exactly what we do. This is very useful, right? At some point, we can decide. This is how we do reconfiguration, if you're familiar with reconfiguration. It's kind of similar. If we agree now in block 5 on something, that's what we do. We look at the history, let's say a window of like 10, 100, whatever makes sense, block in the past. We collect some metrics, like for example, how was the participated, how many nodes like we actually timed out, how many nodes voted, whatever you want to use, you can collect. Everybody agree on exactly the same information. That's we have consensus, right? And then we can apply some deterministic function to determine, to decide who is going to be the leader in the future. So this is exactly what their idea. This is exactly what they did. They said we look at this window. We say that the Australian node keeps struggling. We keep waiting for him. The Australian node is not going to be the leader for the next 1,000 rounds. And we move forward with that, only with strong leaders. And this alone improved performance by a lot. Much more than the debate whether we're linear, quadratic, much more. This is like a very good production optimization. Yeah, and like I said, we published the paper after the fact explaining why the engineers are so smart. Okay, fast forward. Oh, yeah, sure. Sorry, yeah.
That causes centralization.
Did you guys have fun?
Is that going to lead to some centralization
Well,
in some way?
maybe, but first of all, you want to go down the road of defining decentralization. We can do that, but even I will argue that all the validators have the opportunity to contribute. If you don't want to buy the hardware to be fast enough to contribute, then you're going to suffer from some penalty. And it's not like we're going to keep you out forever. The solution was that we are going to reduce the probability of you becoming a leader. Like, this is how it is.
They have an ocean to overcome. It's not how.
Well, life is not fair. They can move their validators to Europe, Yeah, but I mean, to your point, it's a legit criticize. I guess there's always a trade-off, right? There's always a trade-off. There is a performance decentralization trade-off here. I agree. But my talk is not about decentralization, and I'm not going to go to this philosophical discussion of what is decentralization. There is a Clarity Act right now. They are discussing it in Congress. What decentralization means. Okay, so 2022, unfortunately, the Novi project never launched, even though we were repeatedly, it was also funny, like every 2 weeks they said 2 weeks, 2 weeks, 2 weeks. Actually, Alberto was very smart. He told me half a year before it was killed, it's not going to happen. I'm like, come on, Alberto, like, be optimistic a little bit. They keep saying that it's going to happen, I believe it. You don't have enough experience here, trust me, it's not going to happen. Yeah, he was right. So yeah, at the beginning of end of 2022, when Novi project was completely killed, unfortunately, you can go and read on Twitter David Marcus' post. It's very interesting. From like about a year ago, I explained in details what exactly happened. Very great man. Yeah, if you are interested in this drama. Anyway, bunch of us moved to Aptos, and we continue working on the same. It was an open source, luckily. Everything that we did there at Novi, we took the open source and we built Aptos, which purpose was to have a high performance blockchain. Now, high performance is a different game, right? It's not. It's no longer a question of like one transaction per day. We had to compete with we had to compete with Solana. We wanted to really like in the high performance space. So we came, this time we actually like are motivated to improve latency, and we start working on it seriously. So the next thing we immediately ask yourself for your question is like, what is this linear? Do we really need linear communication? What's the real impact of that? And very quickly we realized that it doesn't have anything. For our setup, 150 validators, like I said before, if you have thousands, maybe it's a different question. But for our setup, it did absolutely no difference, quadratic or linear. Something else, which I talk in a second, did a huge difference, but not that. So immediately we moved back to the BFT approach, 3 hops, which, I mean, still, we are reinventing the wheel, but with a little twist, right? So we still kept the pipeline. And so basically we call it Jolty and Star because we never published it. It's not like, it wasn't published in an hour. We thought it's incremental and it looks like BFT, we didn't even try. So, but we still did the change, and internally we call it Jolty and Star. It's PBFT common path, PBFT recovery path, but it's pipeline, which, like I said before, we like this topic. And the takeaway is that performance is hard to estimate in theory alone. You have to run the experiments. You have to sometimes, unfortunately, invest a lot of money because these geo-distributed experiments are expensive. Like I think for the system, for novel papers that we published, I'll talk about it later. What was it? 100K we paid? Something like this. 200K. Yeah, it's crazy expensive to evaluate the systems. Which is unfortunate, but simulation is not going to give you that. You actually really need to run it on a geo-distributed real environment if you want to actually see how it behaves.
Sasha, the pipelining was every two network layers.
Yes, at this point, still every two is same as at this point. Yeah. Okay, now, Itai had a perfect question. Let's see where the end-to-end latency coming from, because this is again one thing that you realize when you start to really care about latency, because at first, like as a theoretician, I cared about, okay, the leader submitted block. How much time, time it's already not very theoretician, but how many hops will pass until the block is committed, right? That was the question. But in reality, it's not the case. You have a blockchain, right? So in reality, you have another hidden latency cause. You have 3. You have queuing, dissemination, and ordering. Now, dissemination and ordering are intuitive, everybody knows what it is. Queuing is the tricky one. So let me explain. In the end-to-end, in the blockchain settings, you have the clients. Clients are big transactions. At some point, this transaction reaches the validators. I'm not going to talk about this latency. It's also from the client to the validator, it adds to the client experience latency, but we're not going to talk about this today. It's outside of the scope of the BFT alone. From the BFT point of view, the end-to-end latency of PBFT is from the time transaction arrives to the validator until the time the transaction is ordered and the block moves to execution. Right? So we have 3 latency cores. Queuing, which is the tricky one. It took us some time to realize it's there and like pay attention to it. So this actually goes back to the block time. Here the block time actually pays, it's important because it contributes to the overall end-to-end latency. So for Itai's question before, a new block will be submitted every 2 hops, every 2 message hops. So a question for you, what does it mean for the queuing time, right? Transaction arrives at some point here, and will be included here, whether it arrives here, here, or here, right? It will be included in the next block. So I'll answer for you, right? If every block goes into hops, on average, the queuing time is 1 hop, right? I mean, assuming like not like what is the distribution? Yeah. So this is important because when you talk about end-to-end latency for blockchain, you want to know how much time from transaction is submitted until you're committed. If I only talk about this latency, I'm forgetting about big part, and then you come to the engineers, you tell them, look, my theoretical paper says this latency, you say this latency, you don't know how to implement anything, right? You have this stress. So you need to understand and like really like where everything comes in the system. So yeah, this is the queuing latency that I explicitly decoupled dissemination from ordering because it's become important, because dissemination is actually not part of the ordering. You are ordering metadata. You're disseminating data. This is like a very important observation I will touch in a second. But here on this protocol, you can see queuing is from the moment transaction arrives until it proposed. Dissemination is this one hop in which the data is disseminating, and then we have another two hops to commit the transaction. So if we talk about our previous consensus, here the leader is going to send the block to everybody. This is dissemination, then signatures, block is commit. Okay. Johnson star is another internal name where we improve this latency. Now, we didn't think about this idea. We borrowed this idea from Moonshot. Very clever idea, but we implemented it, and internally we call it Johnson++. And the idea here is to reduce the queuing time. Now we are proposing a block every hop. That basically we're reducing what is called the block time, right? Instead of having two hops, we are doing it every hop, and the meaningful advantage of that is that we reduce the queuing time on average from one hop to half a hop, which might feel not significant to you, but you know the latency fights over the consensus protocols and companies is very high. So even if you reduce 70, 100 milliseconds, it's huge money. So yeah, any questions about that? No, queuing latency is clear? Okay, good. Yes, wait, let me tell you how we do it. So, just the intuition, before, we had the leader proposing a block, then everybody signing it, and then the next block links to this QC and continue with the block. Now here, we don't have a QC at this point. The leader proposes a block. The next leader sees the block as it is, without the signature, yes, they cannot be confident this block is going to be committed, so we optimistically link to the block. And here, when the next time you need to decide whether to pick optimistically this proposal or not, you already have the QC for the previous block. If it indeed managed to collect the QC for block 1, the leader over here can optimistically link to block 2. If not, timeout, recovery path, the regular story.
Sasha, do you have sort of slow recovery paths in exchange for the short
No,
time?
same recovery. Okay, and in production it works well. We don't see any issue with that. Most of the time, the optimistic path works. Okay, so enough with latency for now. We'll come back to latency soon. But also, as we continued our journey in the blockchain space, at some point throughput became very important. I don't know how many of you guys follow about all the crypto Twitter, but at some point everybody started throwing numbers. You know, we do 10,000 transactions per second. No, we can do 100. No, we can do 1 million transactions per second. You know, everybody threw numbers. It became an arms race, or like everybody were working. How do we increase to? Okay, that was the goal. We shifted from latency to throughput. I mean, we don't care about latency anymore. Just give us throughput. We don't care. Like a minute ago, we were all working on latency. Now it's throughput. You have to follow the narrative. Nothing. I mean, you have to do what you have to do. Okay, so throughput. How do you increase the simple observation here, which is surprisingly took some time, but maybe not surprisingly, because maybe before people wasn't really challenged with this challenge to improve throughput dramatically, so they didn't pay a lot of attention from this practical point of view, because the observation is not like groundbreaking, right? But if you think about it, if you have a leader-based approach, right, in which a leader sends the block and everybody else kind of agree and endorse and sign it, the leader is the only one disseminating transactions to the system. So simple logic. If the leader has a limited bandwidth, if the leader can push, let's say 1,000 transactions per second, you cannot magically commit more than 1,000 transactions per second, right? This is what the leader is pushing, that's what we are committing at the best case, right? So the observation was kind of clear. We have to disseminate data in parallel. If we don't disseminate data in parallel, we are limited by the leader bandwidth, there's really nothing we can do. So let's now think how we disseminate data in parallel. So this brought us to explore the DAG-based BFT. Alberto will give a talk dedicated to DAGs tomorrow. I'm gonna just spend a few slides, and yeah, hopefully you can get some intuition from my talk as well. So the DAG is, I don't know how many of you are familiar, but the idea here, if you see the pattern, it's all-to-all pattern. It's still the quadratic pattern as before. I just added this little section here to the, so it looks a bit different, right? But the communication pattern is the same. The difference is, and we chose, it doesn't need to be round base, but round base is much easier to like kind of think about. So we are going to talk about round base DAGs here, which means that we are moving around. The difference between before, when I just saw a quadratic communication, here, we carry the structural information. Like these nodes over here carry the information of the links here. So when we're building a DAG asynchronously, and when I propose in submitting distributed my node, I'm going to link 2f+1 and -f nodes from the previous round. Why 2f+1? Because it's asynchronous. In total we have 3f+1, so the standard, you cannot wait for more than 2f+1. F can be bad, crash, whatever, right? So that's the most we can wait. In an asynchronous environment, we can always assume it will arrive. Again, in theory. Not in theory, complicated stuff. But at least this is how we thought about it. And this is the DAG. You basically keep building it. In every round, you wait here to receive n-f nodes, you link to them. You create a node, you send it out. Now here is also interesting distinction. The DAG can be certified and uncertified. In an uncertified DAG, means that I just send my node. I send my node, and like in standard BFT, I can lie about my node. I can set a team one node, I can set a type different node, it can link different things, and the protocol will need to somehow deal with it. Like, Alberto will talk about it more. The other option, and it's much faster, it's just one hop to publish a node. Another option is to have certified DAG, which means that every node here is reliably broadcast. It can be consistent broadcast, it can be reliable broadcast, but the point is that it's not going to take one hop, it's going to take a few more hops, but the proposal of the block, the node, the validator that proposed the node cannot lie about it. We kind of all agree, if you're familiar with reliable broadcast, it means that everybody will see the same node. It gives us a very interesting property here that will be very useful to reason about, is that if I see a DAG and you see a DAG, it might be not exactly the same DAG because some nodes you already received and I don't, but what we both received is going to be exactly the same and the structure is going to be exactly the same. So, so with this, yes, Narvel. Narvel is a protocol we worked at Novel, started Novel, to increase the throughput. We already started the research over there. And the idea was there, we weren't thinking at the time about BFT, about public consensus. We had this issue, our mempool implementation was very bad. The shared mempool implementation was very bad. We wanted to improve the shared mempool implementation. And we already had the observation that data dissemination needs to be in parallel. So we're thinking, let's build the DAG. We anyway, our implementation of the consensus anyway shared the data quadratically. Like if validator gets some transaction, the original implementation was, let's disseminate the transaction to everybody, so all the leaders will have the transaction in the mempool, and then the leader will pick the transaction. So we already have this communication, but we said, let's build the DAG from this conversation, but let's link it together. It's gonna be, we had this strong intuition, it's gonna help, it's gonna work. And the original idea was that we're gonna build the DAG asynchronously. And we're still gonna stick with our consensus. It wasn't this consensus, but for the illustration of the, it doesn't matter, right? And what we're gonna do at some point when I'm the leader, it's my turn to propose. I look at my DAG, my shared mempool, and I will propose one node. That's what I'm gonna do, and then agree on the node, and then we're gonna go and commit this node together with all the causal history. I basically like most of the shared mempool. And the reason we can do it, because like I said before, if the DAG is certified, everybody will agree and have exactly the same causal history from this. So we're gonna run this consensus in the background to agree on this. And yeah, that was very cool, but while we worked on it, we had this realization that DAG is actually all you need to solve consensus. Why is that? Because, like I said before, the DAG carries the structure. It doesn't really, remember the PBFT diagram? Looks the same, right? So why can't we send consensus? We have all the information. DAG carries all the information of the votes, right? It's just the same. So if you treat the vertices as proposal, if you treat the links as votes, and then you look at your local DAG, it's like you can think about it. This is basically a BFT or any other protocol, right? Consensus right here. Let me just interpret the DAG in a way that makes sense to me, and I will just be able to commit stuff. And so at first we thought about it like from a synchronous point of view. We came up with a synchronous consensus. Still, still at Novi, still the theory work, right? Let's do asynchronous, why not? And the simple observation was that we're building this DAG. This is the intuition for the asynchronous protocol. We have enough intersection over here. Again, I'm not going to go to the details, but you see a lot of messages, a lot of intersections over here that if any of these nodes would be, we would treat it as a leader, we would have enough information somewhere over here to commit the leader. Just trust me on that. There is like enough of all intersections over there. And then, so this is what we did. This was the idea. We just run it. And it's asynchronous. We cannot solve it deterministically. We need randomness, right? We need a coin. So this is actually the idea. We're running. The adversary at this point doesn't know which one is going to be the leader. He can play with the messages as much as he wants, but no matter what he does, he will need to commit to n-f nodes, which at this point of time would have to be committed if they chose it to be the leader. Just, there's no other way. The adversary is limited here. This is how we treat the adversary. And then we flip the random coin after we're already here, like we use these nodes to piggyback some random coin mechanism. And then we choose one node at random with probability 2/3. We'll choose one of them and we can commit. If we commit, very good. If not, we're going to need to try this again. The expectation, we will do it all one round. So this was the observation. And then with that observation, we came back to Narwhal and we published, we built the system, the first DAG-based system, Narwhal and Task, which had asynchronous consensus with zero overhead. I said zero overhead here is that you build the DAG and that's it. You don't need to do anything else. You don't need to send the node to an auxiliary consensus node. The DAG by itself is already enough. We at the time thought it's very neat, it's very cool observation. Then the more you think about it, you understand why this is obvious. There's like, okay, sure. But at the time we thought it's like really clever, we're really proud of this work. Again, parallel dissemination inherently, because the DAG is like inherently parallel, right? Everybody in parallel publish their nodes, so everything is parallel data dissemination. And we had this impressive number of throughput, 160K transactions per second. At the time it was very, very good. But what's the problem? The latency was very high. So we're back to square one. We started from reducing latency, then we shifted back, the industry shifted to throughput. We came up with a very high throughput protocol, but the latency was much higher than the original starting point. So, okay. What do we do now? Improve latency again. What else do we have to do? Okay, so the first candidate is let's get rid of the asynchronous protocol. We don't really need it in production, and partial synchrony is like perfectly fine. And this is how we came up with Bullshot. It's the same idea. You have to build the DAG asynchronously. It just, the way you change a little bit the assumptions. You don't assume a strong adversary that much. You assume that eventually everybody will agree on the leader, and we can kind of align it. And this is why we first, we don't need the randomness. Second, we can commit in much shorter time. Now I ask you a question, what you want to do? Because usually when I give a talk about Bullshot, I claim I can explain the entire protocol on one slide. This is the slide. I can do that, and we can spend 3-4 minutes. But if you guys think that there is no way you can follow the details, I'm not going to do that. I actually remember these details, so I think I can explain. So, any preferences? I just don't want to stick to myself, right? So, if you guys think it's a good idea, I can do that. Somebody will need to take responsibility. Good? Yeah. Okay, cool. So, we have the DAG, right? We build it asynchronously. 4 validators, 12 plus 1. Yes.
So before you go into that, when you measure throughput for these stack protocols, does it account for the fact that there is wasted throughput because the same transactions get through?
But no, why would we do that? We published the paper. Why would we do the stupid thing?
But yeah, how much of a concern is that in the...
I believe it's a concern. It's a real concern, yeah. We never ended up deploying a DAG in production. I will talk about it. So, if you have a question for tomorrow, ask Alberto and see what he has to say. I believe it's a big concern, yeah. partially the reason why we never deployed it, but there are other reasons as well. Okay, so we go for it. So this is the DAG, similar as before. We're building asynchronously. Every node in the DAG, you see, links to 3f plus 1, right, nodes in the previous round. Yes. So here how high-level bootstrap works. We need to have a predefined mapping. It's not an asynchronous consensus anymore, it's partial synchrony. So we have a predefined, everybody agreed mapping of leaders to rounds. Everybody know that round 1, this is the leader, we call it anchor in the paper. Everybody knows that round 3, this is the leader. Everybody knows that round 5, this is, right? It's not gonna change. This is the, I mean, it can change, but not now. For now, it's not gonna change. Okay, now the commit rule is very simple. I look at my DAG. If I see that this is the leader, this is the anchor from round 1. If I see f plus 1 nodes in round 2 vote for it, by voting I mean link to it, I can commit it immediately. The intuition, why is it good, is because if I have f plus 1 linking to it, it intersects with any 2f plus 1 from the next round. So every future leader will have a path to this anchor. It's possible that you see this is my local view of the DAG, right? I cannot commit this. Actually nobody can commit it, because I see all the nodes, right? There's no surprises here, I see all the nodes, but I have only one link over here, I cannot commit it. But yeah, this line is not the best for this, I probably changed it, but imagine I didn't see this node, right? So in my local view of the DAG, I would see 1 vote out of 3. Sorry, no. Forget about it. You see my details, it's hard. Yeah? Forget about it. It's a good example. The votes come from here, right? So this is the node. I see 3 nodes out of 4. I don't see this one in my local view of the DAG, and I see 1 vote. I cannot commit. But maybe Itai over here, he got more lucky a little bit. He already received this node, and this node links to this the leader as well. So in Itai's local view, he has 2 votes, right? Itai can commit. So Itai knows for sure any future leader will have a link to this leader. I'm good, right?
You need 3 votes.
No, f plus 1 is enough. Because f plus 1 will intersect with any 2f plus 1. That's because it's not, the standard will be, BFT is 2f plus 1 and 2f plus 1 because you have malicious and you have 1 good intersection. You don't have malicious here. The DAG is certified. I cannot lie about the node. That's the point. This is why we can do f plus 1. So, yes, so if I see 2, I can commit, if not. If I commit, good. I commit this non-anchor, I commit all the causal history, I move on to the leader of the next round and I try that. If I don't, I still need to determine whether I commit or not to this node. This is the tricky part here, and then this is question for me. This is my local DAG. I don't know what to do with that. That's question, right? I'm gonna go and commit next leader. Now next leader I don't even have it. I cannot commit it. Obviously 0 votes. I can't even commit it. I'm gonna go again, try again. Let's try here, right? Now here I'm happy. The leader is good. I have 3 votes. Good. I committed this. Now the safety trick is that if I go back, if I see a path from this leader to this, I can commit. I don't have a path, right? So I don't commit if I skip this leader. This leader is out of the blockchain, skip. But I do have a path here. So I'm going to commit this leader. And remember what I said, if I committed this leader, the intersection that f plus 1 is commit rule with the 2f plus 1, votes that we have on constructing the DAG guarantee that even if I don't, and I commit this but not this, I will have a path. So I will cross commit this, because you see, because I committed this, right? I did it as well, so we all agree on the same ledger. Then I go and commit this, and when I commit this, I go and commit all the causal history. The reason that I can do it because it's deterministic. Like I said, everybody see the same causal history. If you see the same node, it's going to be the same node. If you see the same node in the same position, it's going to be the same node. So I can safely commit all the causal history, and that's it. That's the entire protocol.
I'm not sure if I understood. I didn't understand. So why you can commit the A1?
A1?
Yeah.
Yeah, the thing is that I need to be safe. I need to be safe, right? I didn't have enough votes, but I don't know whether anybody else had enough votes, right? And at this point, like I said, somebody here could have this node, and this node could have linked here. I don't have it in my local view, I don't know. Right? So I need to be careful about that. So when I commit this, I need to ask myself a question. Is it possible, right, that somebody committed it? The answer is yes. So I have to go and commit this. Just for safety. Yeah, it's part of the history and it's indeterministic. If we all agree on this, we will all agree that there is a path to this, right? So we just follow the deterministic rule that will make sure that if everybody, if somebody commits this, I will also do. I will move on. I think I was okay. Something. Okay. Let's think about the latency, the actual latency of Bruchel. So 3 hops per round to certify a node. The way to certify the node is a consistent broadcast. The proposer sent the node, everybody signed and send the signature back to the proposer. The proposer aggregate the signature. You see, it's always the same. It's the same pattern always, right? the proposer aggregate the signature and disseminate it back to everybody else. This is already the first message was uncertified node. The third message is already a certified mode. It comes with a certificate. The certificate is very strong. That means that the proposer cannot lie about the block. And it also means that it's important that if I don't have the node, but I see the certificate, I know that I will be able to fetch it. Like I'm confident it's in the system, it's available. If F+1 signed it, F+1 would know that they signed it and they guarantee to store it, everything. But still the latency is 3 hops. Now 2 rounds to commit an encode, a leader. One round is to publish, in the good case, another round to collect the votes, right? And then that's also tricky, 1 round to link to an encode. Right? Here, it's 2 rounds to commit this, but what about this guy? Right? They require the next round to be linked and to be committed as part of the causal history of the leader, right? So we can't just say, oh, the latency of the protocol is 2 rounds, it's 2 rounds because we can commit the leader in 2 rounds. No, because there is another extra round by everybody else to link to the leader, right? So, so the true on latency is going to be 1.5 hops on average for queuing. Again, this is because to certify, to publish a node is 3 hops, right? To certify, we take half of it. This is the average time, the queuing time from the if transaction arrives at a random time in between these 3 hops. Dissemination is 3 hops to be linked to the leader, like this is dissemination. This is dissemination to be linked to the leader. And then ordering is 6 hops, 2 rounds. So overall, 10.5 hops for most transactions. Still very high. Remember,
6 hops are from Ulster.
No, nothing to do with WhatsApp. 6 hops is because to ordering, I call ordering to commit an encode. What does it take to commit an encode? I need to publish the node, and I need to I need to have the votes. So 2 rounds on the DAG, and every round on the DAG is 3 hops because I need to certify the nodes because the nodes are certified. So this is 6. Yeah. Any more questions? No. Okay. Overall 10.5, still very high. I mean, no, unacceptable, especially because when we propose it to our engineers, it's like, I mean, this is very good work, good job, but our current consensus is 3 hops. You want to deploy something 10 hops, it doesn't make any sense to us, and you know. Okay, so good. We have jobs for, another year, we have something to do. Let's improve the latency. Short and Short++ are the protocols that we came up with later at Novi. Other people, by the way, worked on DAGs and came up with different optimization, sometimes like resemblance, sometimes not. Many ideas over there. I'm going to describe this because this is the one I know. Okay, so we tackled the latency from 3 different angles. There is this queuing, dissemination, ordering. We said, if we want to do something reasonable, that the engineers will ever agree, each one of these is too long. We need to just everything. We need to shave everything. Let's see what we can do, and hopefully it's going to be reasonable enough for deployment. So we ended up with 3 optimizations. Let's start with the first one, the algorithmic improvement, which is funny because this is very easy, but we didn't see it. We didn't see it at all. We worked at Bullshard, at Novi, we didn't see it. We worked on Short, we didn't see it. And other people cited bullshit. It's a highly cited paper. Nobody saw it, and it's like when you see it, it's like so surprising. Like it's so simple. How can not? And the takeaway is that when you deep into the detail of something, at least for me, you can just not see something very simple because your mind is kind of sure this is how it works. You cannot do better. I tried in the past. This is it, right? And you don't challenge yourself. So it's always good to have interns. It's always good to have like new people to work on to look at this. If they are smart, they will always find something. And this is one of these. One of these stories. We had Sohav as an intern. Supposed to be here tomorrow. I think give a talk. So tomorrow, yeah. So he was working on something else, like some. I will talk about that tomorrow. Speaking of the generation. But one day he comes to me and said, "Look, I can improve bullshit latency." And like, really, how? So then I wasn't taking it seriously, honestly, because I thought about this protocol so much, and And he said, "Look. You are looking at the DAG now, and you are looking to this node, certified nodes, and you are looking for F+1 to commit them. The uncertified nodes, which you receive immediately after one hop, before the 3 hops were certified, carries enough information for you to commit." He said, "You need F+1 to commit with this node, right? But if you actually receive 2 F+1 uncertified nodes, like request to certify, before they are certified, it's actually enough because F+1 of these nodes are honest, they were eventually certified. Eventually your original commit rule will be satisfied. You can commit 2 rounds before." I mean, I talked about it for 5 seconds and I said, how did we miss it? It's like so simple, right? How did we miss it? And it was very nice. In some weird situation, you might still receive the F+1 certified node before you will receive to F+1 uncertified. It can happen. So what we end up doing is taking the best of both, whatever comes first. And this is how the commit rule, we reduced it from 6 to 4. That was really, really nice. And observation and a good lesson for everybody. You cannot take things for granted. Everything can be improved as long as, if you don't prove a lower bound, and the lower bound is well defined, everything can be improved. Many lower bounds are not well defined. Okay, architectural improvement. We said, remember this queuing latency? Because we insist on certified DAGs, because we like the properties, you don't have to do that, there are other solutions, but we insist on certified DAGs, it gives us this 1.5 hops you just use on average in queuing. Because you can propose a new node every 3 hops. How can we deal with it? So we had this idea that can be applied to any protocol if we want to reduce, and in theory you can reduce the queue latency to 0, but obviously it's not going to work. But what you can do, what we did, is instead of having 1 DAG, we run 3 DAGs. Every hop, and we are going to synchronize that, so that every hop, we are going to propose a node in the next DAG. So we're going to have 3 DAGs in parallel. I'm going to propose a node here. In this world, I will need to wait 3 hops to propose my next node. But after 1 hop, I'm going to propose the node here, and after 1 hop, I'm going to propose a node here. We're going to run 3 DAGs in parallel, and then the consensus is going to be on top of them. So the first block is going to be constructed from this DAG. The second block is going to be constructed from the decision from this DAG, and so on and so forth. So this simple observation allowed us to reduce the queuing latency, and theoretically you can have like 100 here and divide the queuing by 100. Good luck synchronizing all of that, but at least in theory you could do that. And we did that, and it worked to some degree, at least for the system that we needed to publish reasonable results, it worked. In production, well, very tricky to synchronize DAGs. But we thought it's a cool observation, and I call it architectural improvement. Okay, the last one is engineering improvement, which also required some, another of these observations that how come we didn't see it before. This time we didn't do an intern, we actually thought about it ourselves. But yeah, it's another of these, like I looked at this protocol so much, how come I didn't see it before? And the idea is very simple. So first of all, what are we trying to improve? Like I said before, we have an anchor, we committed in 2 rounds, but these guys we cannot commit, right? They need to wait more rounds to be linked to a new anchor and then committed. We want to get rid of it. We want every node to be an anchor. That's what we want to do. That's how we completely get rid of this 3 extra hops in bullshit of connecting. The way we do it is, again, understanding we have a consensus. if we have a consensus, we have a point on time in which everybody agree on the state, and we can do whatever we want. We can even decide to forget bullshit and switch at this point to hot stuff or to any other protocol, right? Because this is exactly what consensus gives. It gives a point of time when everybody agreed. You can deterministically at this point do whatever you want. So with this observation, we said, okay, I know I need this entire DAG to decide whether to commit this anchor or not this round. But after I did that, and the safety of the original bullshit protocol guaranteed that everybody will agree at some point, maybe later, maybe sooner, at some point this node needs to be committed. Now I have freedom to do whatever I want. And what we decide to do is just say, instead of in the bullshit protocol, we're gonna say the next leader is gonna be somewhere here, right? We're gonna say, no, the next leader is the next leader. And after we commit this, we're gonna say, no, this is gonna be the next leader. So this gave us the ability, in the good case, commit everything very fast, because we use the same goals, but we interpret the DAG in a different way every time from a different point of view, like who is going to be the leader, and this is what we can do. Now, in practice, it's not very easy, so it requires some engineering challenge, because if, for example, one of these nodes, let's say this node, like, doesn't have enough votes over here, and I need to wait to grow the DAG in order to decide what to do with it, all these nodes in the future will suffer from the latency, and we are not gaining much. So there was an engineering challenge to make sure that we wait for as much possible here. We can't anymore move the DAG like in network speed in order to grow the DAG. We need to introduce some timeouts and synchronize and wait. In practice, what you would do is arm decentralization and say, I don't want to wait for everybody. I'm going to use some leader reputation, and I'm going to just wait for the strongest and move on with them, and hopefully it's going to be well distributed enough so it will cover like most transactions. And yeah, that's what, but we never deploy that. Too hard to synchronize. Okay, overall short plus end-to-end latency is 4.5. It's matching the current consensus if you took queuing into consideration. And that's it. So, like I said, like BFT systems become very popular at some point. We did a bunch of works, others did a bunch of work, became very popular. The good properties is that some of them are deploying production, deployed to Bootstrap and it's safety, right? Yeah. And Alberto will talk about the training tomorrow, I'm pretty sure. And inherently high throughput, you do nothing, then the DAG for consensus, and it also gives you some sort of censorship resilience by nature, because you have all these like many proposals. And the bad thing, at least for us, was that the latency robustness trade-off. Like for our case, in certified DAGs, it was very hard to achieve this latency in practice without sacrificing robustness. It's hard to synchronize it. You saw the improvement that we did. It worked very well in the paper. The results are great, right? Throughput, if you check the paper, throughput is very good, latency is also very good. But once you go production, you will see it's very hard to maintain and synchronize it. And we thought about it and we said it doesn't worth it. Instead, we decided, shortly we'll talk about, oh my God, I'm running out of time, but it's okay. I think I have enough. I will talk to you what we did. I will tell you what we did in the eventually did. For the uncertified DAG, we also didn't go with it. There were also very clever ideas over there. There are other issues. Fetching on the critical path become an issue because when you certify the node, like I said before, this node is available. If you get the certificate, you're confident, you can get it later. You have a proof of availability in some way over there. When the DAG is uncertified, if somebody sends me a node and it's uncertified, and expect me to link to this node and send my node in the future, I cannot link unless I have the node. Because this guy might be malicious, it can only send it to me, the other it can equivocate, and then if I continue like this, eventually we can stuck. We will stuck by trying to execute some node and nobody has it, nobody can fetch it. So it requires some critical fetching, which I'm sure can be overcome in practice in one way or another, but we decided not to continue with the DAG, and instead we went back to the leaderless, to the leader-based approach and try to apply everything we learned and all these insights over there. So yeah, go back here, back to square one again, right? We're back to a consensus protocol that has good latency. We're back to improving throughput, right? Like always, throughput, latency, throughput, latency. Question? No, okay. So we still have the observation. Parallel dissemination need to be made. Dissemination needs to be made in parallel. But you don't have to. You don't need to DAG for that. DAG is one way. It's a good way, but you don't need the DAG. You just need to disseminate in parallel, right? So why not have the consensus layer same and add a component in front of the consensus just to disseminate data? It's like immediate application of Nowgirl. And the dissemination layer will be the following. Everybody in parallel will send batch of transactions. I receive the batch of transaction, I sign it. By signing it, I guarantee to store it, persistent to storage. Then the issuer of the batch will aggregate the signatures. And this quorum certificate is a proof of availability. If I show you this certificate, you know there is a supermajority of nodes that has the data. Even if I myself don't have the data, I'm confident I can get the data, right? Under the assumption that they're actually doing what they're supposed to do. And then we'll take this proof of availability, disseminate to everybody else. And then the leader will look at it like local mempool and will take this proof of availability and propose them in consensus. The leader will no longer include big data in its proposal. It's going to be just this proof of availability. So the leader bandwidth is no longer the bottleneck that it was before. And it works very well. We could scale it, DAG level throughput. The problem is that we have again high latency. We introduced 3 more hops before the consensus and 2 queuing time. We have here queuing time, and now we have here queuing time. And yeah, unacceptable again. Luckily, at the time, everybody were advertising like high throughput, so we actually deployed it. But we didn't really need to use it because we had a hack in which if the throughput is below something, we bypass and we directly propose the transaction in consensus. We had it running in the background in case the demand will come. The demand never came, and in practice, at that point, we just run regular consensus with this in the background as like a backup. If the demand somehow spikes, we can handle it. Okay. So we tried to reduce the latency. That was the goal. This is how we moved on to the Aptos page protocol. We have 2 variations. Page Aptos is the simple one. The full Aptos is more complicated. The simple one is very simple. Before, everything is the same. I send everything, everybody sign, aggregate the signature, we send it again. Like consent, it's always the same, right? So why can't we just piggyback this on this and do it just together, right? Why can't we do that? And this is exactly what we did. The dissemination layer, instead of having the 3 hops here, like proposing the proof of availability, I'm just going to disseminate the batches, and then optimistically in consensus include the batches without the proof of availability. What it changes now, that in consensus, I can just blindly vote. Because I don't have the confidence anymore that the proof of availability I can repeat. So now it's like a binary vote. If I see like the leader proposed a list of hashes, if I have all the data behind these hashes, I vote. And this is already this is implementation of the previous what we did here, right? This is exactly the same. I vote, I disseminate my vote. If I don't, that's the problem. I need to fetch in the critical path again. Kind of resembles the problem that we have in uncertified DAGs. So we deployed that. And what we do in order for now is that in the background, we also run the proof of availability. And if we have the proof of availability, we always prioritize it in the block, otherwise we are going to use that. And okay, so this is good in terms of latency, but there is the problem in which if somehow the network is not perfect, we will need to do a lot of fetching. That's not great. So here we came up with this interesting idea, is that no longer we need to vote or binary, whether we have everything or not. We came up with this idea that we can vote on prefixes, and we can commit prefixes of blocks. The way it works is that the leader proposes like a list of hashes, right? This is the batches. Now, if I have the first 2, that's all I'm going to endorse. I'm signing the block, but I'm saying I only have these 2. And somebody might have 1, somebody might have 3, somebody might 2. This is what we sign. This is the signature we distribute. Now, when I aggregate the QC, before all the votes were the same, I aggregate the QC will certify the entire block. Now, the difference is that the QC certifies the prefix. And with a couple here quorums. 2F plus 1 signatures certifies the block. but it's inside F+1 to certify the specific prefix in the block. So we have this bunch of signatures. We are going to look at the F+1 signatures that give us the highest certified prefix. So in this example, if I have these, and these, I will certify 2. If I have these, and these, I will certify 1. Wait, I said F+1. I don't need that many. So if I have all these 3, I'm going to take these 2 as my best F+1, and I'm able to certify. And then after we have these prefix wrong certificates, another round, right? It's kind of the same pattern, right? 3 message delay, like in BFT. But and here I will collect the quorum of this prefix certification, and then I can satisfy safety. I will commit the smaller one, and the next round will exchange the highest one. And quorum intersection will guarantee that if I commit something, everybody else will extend at least that. Because if I commit the smaller one, I committed it, everybody else in their quorum will see something which is at least as big as my smallest that I committed, and we have also the, and because they all have to be consistent with each other because they all prefixes of the leader's proposal. This is already too much details, I know that, but we're also very close to them, so I think it's fine. Okay, I'll take a picture. Yeah, I know, I take a picture. I spent like at least 15 minutes on this. Okay. Now, 2026, focus shifts again. We're doing trading now. Wherever the blockchain companies now are doing trading. You know, I believe it show us we can succeed in blockchain. Suddenly, everybody are building DEXs. Right? This is what we see. So if we build DEXs, we suddenly care about other stuff. We care about censorship resilience. We care about fairness. I told you before that defining fairness is very hard. I'm not going to do that. I'm just saying, intuitively for us, if we have a trade somewhere in the world, and you get the information somewhere in the world, we want to give you an advantage. If you sit in Tokyo and you see a ship with iPhones goes down, you want to be able to leverage this information before the person in New York gets this information and we can trade. This is what we want to do. This is what we call by-order fairness. And censorship resilience for us is on the validator level. Like if I'm a validator, I don't want other validators. It's the centralized system. I don't want other validators to censor the validator. Okay, so yes, now 20 seconds. When I came here, I told our CEO I'm going to travel here and he needs to cover the cost. He said, this is not 2023 anymore, we have a limited budget, so you better promote our products, okay? So this is me, where's the camera? Promoting our product. This is Decibel, this is our DEX. The first fully on-chain DEX, moved secured by Move. Wherever you can. Yeah, this is, you can try it, it runs very well. Fully on-chain, everything is on-chain, decentralized, transparent, secured by me. Okay, moving on from this promotion. Is it okay if I take 2 more minutes, 3 more minutes? 2 or 3, okay. Okay, very quickly, before that. So, we came up with this new primitive, which is prefix consensus. With which we can later solve, what does it call? The censorship resilience and order fairness. We believe it's a very cool primitive, like honestly believe it's a very cool primitive. And the thing here is that we have an input, each validator, each participant has a vector input, and it's going to output 2 outputs. And we'll have a lot of, and the property is that every output will have V high and V low as an output, and every V high we're going to extend every V low. It kind of resembles the Aptos intuition, right? And liveness is okay, liveness is always the same, everybody will output something eventually. And the validity is also important that the U low that we output will extend the common prefix of all the honest input. This is the prefix consensus primitive. I know I don't have time, you guys don't, I understand. But I do want to say here that I'm specifically very proud of it because I believe that if you want to get respected in this community, you need to come up with a new primitive. Like this is what we need to do. I showed you at the beginning how many variation and data points you have. You need one with your name over there, otherwise you didn't do anything. Like 10 years of research, you didn't do anything. So this is our attempt to contribute to the next. So it's a new primitive for consensus. Now I have a challenge for your homework. I hope this is a school. So look at the Raptor intuition, try to build this primitive. Try to build this primitive. It's a very nice question for you to see if you can do that. You can develop intuition. You can then check the paper for how we did it, and if you have a better solution, happy to hear about that. And I plan to explain to you how to build from prefix consensus, multi-legal consensus. I'm not going to do that. I don't have time. I don't want to just talk around. You can think about this as well. It's really cool. And just skip all these slides. Just to recap, all this text saying that we improve latency, then we have to improve throughput, then we have to improve latency again, then we have to improve throughput, then latency again, the throughput, and then now everybody is about censorship resilience. So this is this slide. This slide is about how in every generation you think consensus is done, there's nothing else to do, and somehow we're still all here, right? And I guess we're gonna be still here for the next 10 years, maybe quantum computing, who knows, right? And yeah, and with that I would like to conclude this. Thank you for attention.
Questions yourself?
Oh.
There was one slide where you said something about different definitions of censorship resistant, client side versus validator side.
Yeah.
Can you talk about that?
Yes, so what we tackle here is from a validator point of view. I'm a validator, I have a block. I want it to be included in the decision. Okay, I have a proposal, I want it to be included in the decision, then you can define when, right? It can be immediately in this block, it can be a little bit in the future, you can play with the definitions. Itai has a nice paper about that. And then this is one thing, this is for the validator. From the client point of view, the validator itself can censor the client, right? So you have like kind of these two steps. One is assuming the validator is not censoring the client, or maybe the validator is running the app, validator pushing the transaction, and you don't want to censor that. The other part is from the client to the validator. How do you do that? And the approach is encrypted mentally. If you encrypt the transaction, validator can see they can censor, right?
Yes, I was searching here in this prefix based on agreements. It's very 1990s, right? There's also 97,
Like I said,
cheaper 99. Yeah. So you guys are to what you're doing, optimizing something that is from, yeah, it's very.
Okay, go with the paper.
What's
the name of the paper?
I don't know how to check for all of them, but this is the total broadcast.
It's very long. I don't read this paper, but
Just to say, it's nice to see all the ideas coming back.
So when you have this three decks running in parallel, let's say like I want to propose something that's related to something in the array block, do I need to wait until the next array block to do it? Or if I propose something in the B block, like could that get reconciled somehow?
if you want to propose something here, that's related to something here.
Supposed to be in the, yeah, the degrees.
Yeah, so you will have the shared mempool is going to be for all of them together. So the way you usually will see the proposals, right? You will see them after one hop, and then you can optimistically rely on this information, right? You anyway do that when you do pipelining. You don't wait for the block to be it anyway. So you can see what was already proposed, so you don't propose the same. But if you need the guarantee that this thing is already committed, you cannot. But you can.
The next same color.
Yes, but even then, even if you look about consensus today, the block rate is faster than the commit rate. Even then, you cannot do that. Like you see what was proposed, you cannot be guaranteed that it actually is going to be committed, right? You have this problem anyway to some degree. If I understand your question, maybe I don't.
Yeah, I think so. Yeah. So like, I'd like to see a strong guarantee that like something that says block 2 is done, I need to really put that back. Fine.
Yes, but that's unrelated. This optimization is for any consensus, right?
Right.
Okay.
Thanks, Sasha, again.